All right. Okay. Hello, everyone. Welcome back. So, today we'll have two more lectures on basic cosmology. And what I'm going to cover in this third lecture is the idea of inflation and some discussion of alternative cosmological models, since we have already seen the standard model of cosmology. And another running theme in this lecture will be the idea of accelerating expansion of the universe. So we have seen that the cosmological constant or dark energy leads to accelerating expansion at late times. So that will be the theme for discussing alternative cosmologies. And the same kind of acceleration, as we will now next study, is also important at extremely early times, around the time of what is called inflation. Okay, so this particular lecture will deal with this stuff which I had relegated to a tiny corner in the previous two lectures, but now we want to try and understand some of what happens here. Okay. All right, so this is a brief outline of what I want to do in today in this lecture. In the first half, I will discuss some problems with the standard cosmological model the way we have discussed it, and then talk about how these problems can be addressed using this idea of inflation. And in the second half, I will talk about some alternative cosmological models, basically focusing on what is the issue with saying that there should be a cosmological constant in the picture, and what other ideas have been proposed in the literature. Okay. All right, this is a recap of what we discussed already towards in one of the previous lectures on the idea of horizons in cosmology. So I will not go through this in detail again, just to remind you that there is a particle horizon and an event horizon. And in today's lecture, we are going to be more interested in this particle horizon. And remember, this is basically the distance as an observer. This is the distance out to which you can see. And more, another way of thinking about it is that if I start at initial time at t equal to 0, then how far can a ray of light travel? Okay, so this distance is called the particle horizon. And there was also this related idea of the Hubble radius, which will again become important in the subsequent discussion, which is it's almost a dimensional argument to say that I can take the evolving Hubble parameter and construct a distance out of it and call it the Hubble radius. But in at least in the context of growth of perturbations, which we have not done yet, this is important as it sets some kind of a causal scale in the universe, a semi-causal scale, if you like. But in the discussion today, we will see that it appears in a slightly different way as well, in basically in understanding how the particle horizon behaves as a function of time. All right. So with this recap, let us discuss what the standard model fails to do. Okay. So there are a couple of things which are problematic in the standard model. These are historically known since the 80s or so. The first one is not such a big problem, but it has been discussed quite a lot in the literature, so I will spend some time on it. It is called the flatness problem. So here the issue is the following. So if I look at the total density parameter today, okay, even if I did not know that omega k0 is 0.0007 with very great precision, even without that, I could at least argue that the total density parameter omega 0, which is the total matter content of the universe, which I can write as 1 minus omega curvature, this is a number of order unit. I know that it is not 0.001. I know it is not 100. Okay, it is a number of order unity at least, even without precision cosmology. So given this fact, if I now ask what does this quantity look like in the past? So I take all of my matter energy densities and I divide it by the critical density of the universe at some given epoch A being the scale factor, and I construct that omega of A and I subtract 1. What does this look like? This will just be equal to the negative of omega curvature at that scale factor. So if I open this out now using Friedman's equation, what I will see is that, so I will have this omega k will have a 1 over a squared and a 1 over the critical density of the universe. Critical density of the universe behaves like h squared. And then h squared I can again write as h naught squared times a bunch of omegas, okay, with their own scale factor dependencies. So, and then I manipulate a few scale factor powers up and down in numerator and denominator. And what I can do is simplify this expression omega k of a and completely generically write it in this way for a typical standard cosmological model in which there is some radiation, some non-relativistic matter, some curvature, which is of course already there, and let's say a cosmological constant. Good. So now let's look at what this behaves like in the deep past of the universe, which is when the value of A goes to 0. Okay, because today the value of the scale factor is 1. So in the past it was smaller, and you can take the limit as A goes to 0. Clearly, if I have finite values for all of these parameters, in particular for omega radiation, right? So if there is a radiation dominated phase in the early universe, then this term remains a constant while all of these terms in the denominator disappear one by one. Okay, the fastest one to disappear will be omega lambda 0 as a goes to 0. Then the next fastest will be a squared, then the next will be a, and then this one will remain. So now in the numerator, I have omega k times a squared. In the denominator, I have this finite number. So that means that this whole thing, the whole beast, will go to 0 as a goes to 0 because this a is going to 0. So that means omega a minus 1 or omega curvature is going to 0 at very early times. So for example, let's put in some numbers. And if I ask for the situation around the time when the temperature of the universe was 1 MeV, which is an interesting temperature scale in the universe because this is around the time when electrons and positrons annihilated. And it is also the time at which actually neutrino weak interactions involving neutrinos decoupled from the rest of the bath. So some interesting physics happened around that time. And it's also a cute number because the time after the Big Bang that we are talking about is roughly 1 second. Okay, so the reason to use these values is because this is well understood physics. Okay, the thermal history of the universe is well understood at this time theoretically and also experimentally. So around this time, omega a minus 1, according to this argument, will be approximately given by this because I throw away these terms. And now I put in what I know about omega r0 and what I know about the evolution of the scale factor during the radiation dominated epoch, which is what this epoch is. And the number that I get turns out to be omega k0 times 10 to the power minus 15. Okay, so there is a 10 to the minus 5 from here, but a 10 to the minus 20 that will come from here, and the whole thing becomes 10 to the minus 15. So what one is saying is that although omega k0 is a, it may be small or large, whatever it is, but because this is a number of order unity, this number omega minus 1 around 1 MeV scales is incredibly small. Okay, because there is a number of order unity here and times 10 to the minus 15. This is very, very small. And now on top of that, if you go and say that actually omega k0 is also a number of order 10 to the minus 3, then that makes the problem even worse. Okay, so this is the issue. And the question that people then ask is that why was this early universe so finely tuned to be flat? So whenever you see dimensionless numbers in these kind of arguments, which are either very large or very small, particle physicists will tell you there's a fine tuning. Okay, and so there is a similar fine tuning problem apparently with cosmology in terms of the early values of spatial curvature. So spatial curvature did not contribute at all in the early years. So this is an issue. But okay, you can take the point of view, who knows? These are constants which were set by some weird initial conditions. So this is the way the universe behaves. So what if the universe is finely tuned to be flat? You can live with it. It is not destroying any physics. So this is what brings us to the next problem, which is a really serious problem. Okay, it is a problem with our basic understanding of physics. This is called the horizon problem. So here the argument goes in the following way. Consider the co-moving particle horizon at the photon decoupling. So what one is saying is, go back to your particle horizon definition. This is the co-moving particle horizon. Let's assume a flat cosmology to begin with. Okay, so this is all I need to calculate. And this quantity is the value of the co-moving, this is the co-moving particle horizon, the way I calculated from the metric. Okay, so consider the value of this quantity around the time of the photon decoupling epoch. So instead of T0, you put in the value of t, which is approximately 400,000 years after the Big Bang, which happened at t equal to 0, and just calculate this value. Okay, so you can do it in different ways. So, for example, if I use, if I use this kind of expression, instead of z equal to 0 here, I will start at z equals 1100, and then I will take it up to z equals infinity. Okay, so if I do that kind of calculation, in a standard cosmology, let's say omega curvature is said to be very small, omega radiation is whatever it is, omega m, omega lambda, you put to whatever favorite values you have from the Planck experiment or WMAP experiment or whatever. This number will turn out to be of the order of 200 MPC, 180 MPC in the cosmological parameters that I used here. Okay, now you can ask the question, in the same cosmological model, if I calculate the co-moving angular diameter distance to the photon decoupling epoch, starting from today. Okay, so this is the other side of the coin. So the particle horizon is like the distance out to which it's like a physical scale, which is the causal scale at the time of the photon decoupling epoch. So it is like a ruler I want to place in the sky. And now you can see where I'm going because of the angular diameter argument. I want to say that what angle will this ruler subtend at me in the sky? Okay, that is the question I want to ask. So in order to do that, if somebody gives me a ruler and wants me to calculate an angle, I have to first calculate an angular diameter distance, because then I can combine the ruler and divide it by the angular diameter distance and I get an angle. So what is the co-moving angular diameter distance? Co-moving because I calculated a co-moving particle horizon. So I should calculate a co-moving angular diameter distance. The scale factors will then cancel out. So if I do this calculation in the same cosmology, starting from redshift 0 up to photon decoupling epoch, the angular diameter distance turns out to be of the order of 10 gigaparsec. In fact, this number we have seen before also. It is very similar to the particle horizon from our vantage point. But this is now a different distance. It is the angular diameter distance. So if I take the ratio of these two, this gives me the expected angle over which a causally connected patch at the photon decoupling epoch would appear from my vantage point. Okay, so imagine that the universe is composed of causally connected patches at the time of the photon decoupling epoch. Then the photons decouple, they free stream to us. And now these patches are visible to us. And because the patches had a size of 180 MPC, they will subtend some angle at us. And because the angular diameter distance is 10 gigaparsec, the angle they subtend will be the ratio of 180 divided by 10 gigaparsec. Okay, 180 MPC divided by 10 gigaparsec. So do this calculation, it's very easy. You get a number in radians, which is just the ratio of these two things. Then you convert it into degrees. And the answer that you will get is roughly 1 degree. But this now, 1 degree is the expected scale, angular scale, over which the CMB temperature should be coherent. Why? Because you don't expect the CMB temperature to be the same in patches. So at the photon decoupling epoch, what was the CMB temperature in different parts of the universe? You don't expect exactly the same temperature everywhere in the universe unless all those points were causally connected, right? And we just went through a whole argument to calculate the size of a typical causally connected patch. So given this expectation, the sizes of these coherent temperature patches in the CMB sky should not be much more than roughly 1 degree. Excellent. Now ask, what did we figure out from the observations of the CMB temperature? The thing that we started by realizing is that the CMB temperature is basically exactly the same in all the directions of the sky, including like 180 degrees apart. Okay, so forget about 1 degree. The whole sky seems to have exactly the same CMB temperature, up to the tiny fluctuations that are present and which we understand in terms of small perturbations around the mean. But the fact is that the mean temperature is exactly the same everywhere. And this argument would have said that it should not be the same. You should have seen maybe even large fluctuations over angles which are more than 1 degree. So this is the horizon problem. The question is, why is the CMB so uniform across the sky? And unlike the flatness problem, it is not a question of aesthetics anymore. It is a question of your understanding of causality. Okay, so if you do not answer this problem, there is something wrong about the way causality works in the early universe. So this is a really pressing problem and you have to address it. So how can we go about fixing the horizon problem? So in the standard cosmology, where there was an early radiation dominated phase followed by matter domination and even with lambda, etc., this problem cannot be solved. So in order to solve this, let's look at the mathematics of the particle horizon calculation once more. Okay, so this is your particle horizon up to time t. This t is the photon decoupling epoch in our example. Otherwise, it could be any other time that you care about. So if I rewrite this integrand inside in terms of the scale factor, so what I have done is I've just reorganized the terms so that something nice and physical pops out. So here there's a dA over A, and then I have a C by AH. So now C by H on its own is the value of the Hubble radius that I have defined before. And it is a physical quantity, as in it is a physical length, a proper length. Okay, it is C divided by the actual Hubble radius. So, sorry, C divided by the actual Hubble parameter, which is the Hubble radius. So now if I take a proper length and I divide it by 1 power of a scale factor, I get a co-moving length. Okay, that is the way co-moving lengths are defined. Because co-moving lengths are proper lengths divided by 1 scale factor. So this quantity here, C by AH, is a co-moving Hubble radius at epoch A inside the integral. Good. So this co-moving particle horizon, I can therefore think of as an integral over the sequentially progressing values of the co-moving Hubble radius added up over a logarithmic measure in scale factor. Okay, this is the mathematics of the co-moving particle horizon. It is like adding up a bunch of co-moving Hubble radii and the whole thing becomes your co-moving particle horizon. So the fact that the co-moving particle horizon is small, this is our problem, right? The calculation of co-moving particle horizon gave us an angle of 1 degree, whereas I want an angle of 180 degrees. So this calculation is not giving us a large enough number. So why is it not giving us a large number? The reason is that the behavior of the co-moving Hubble radius at early times when A goes to 0, this is not the way we want. It is not giving us enough contribution to this integral at early times. Okay, so for example, during radiation domination, the co-moving Hubble radius C by AH is proportional to A. So as I take A going to 0, I get lesser and lesser contribution. Okay, so there is not much being contributed at early times by this integral and integrand, and that is why the whole integral is not building up to a large number. So people thought about this in the 80s and argued that one possible way of getting around this is to maybe allow for a brief phase in the history of the universe where you don't spoil any of the nice predictions of Big Bang nucleosynthesis or the thermal history of how neutrinos decoupled and all of those things. You go earlier into an epoch which is not experimentally tested, and there you have some freedom to change the theory, okay, because you are not under any experimental constraints. So maybe in such a phase, in such an epoch, you can allow for a phase in which previously causally connected points become temporarily causally disconnected. Okay, so imagine if such a thing were possible. Then why is this useful? Because then it would mean that temporarily these patches became causally disconnected, and in the meantime you can change the distance between these patches by a large amount, and then eventually radiation dominated phase will come in, and then the patches will again become causally connected, okay, as light travels out further and so on. So how to do this? And because if you can do it, then you may be able to solve this problem. You can increase the size of the particle horizon considerably. So how do you do this? Just looking at the integral, it is clear that the only way you can achieve this is if the co-moving Hubble radius, instead of increasing as a function of time, for a short amount of time, it should decrease as a function of time. Okay, because then you can arrange for this business of the contribution to the particle horizon at that time will increase substantially, and you will be able to produce this causal disconnectedness for a short time. Okay. So we want this C by AH to decrease as a function of time for a short time, and thereafter then it can go into its increasing phase, and then starting from a total integral which is already built up to a large amount, and then you can go ahead from there. Okay, so how should one set this up? So mathematically, if I want C by AH to be a decreasing function of time, then it means that its time derivative, so the time derivative of its inverse. Okay, so C by AH is a decreasing function. So A times H has to be increasing. But A times H is A times dA over dt over A. So this quantity has to be increasing. So its time derivative has to be positive. But if I now just stare at this expression, the A's cancel, and basically I have the second derivative of A, which has to be positive. Okay, so after all this rigmarole, you have come back to a very interesting situation where now the horizon problem in the early universe is demanding that at least for a brief period, the scale factor of the universe should be accelerating. The expansion of the universe should be accelerating. So this kind of phase of rapid accelerating expansion was given the name inflation. And for example, one possible way of generating such a situation is something that we have already seen, which is something that behaves very much like a cosmological constant, in which nothing else is there in the Friedman equation except a cosmological constant. So h squared becomes proportional to the cosmological constant, and therefore h becomes itself a constant. And if h is a constant, then the scale factor will increase exponentially, and therefore obviously it will be accelerating. Okay, and the corresponding co-moving particle horizon, sorry, the co-moving Hubble radius will decrease as required, and in fact it will decrease also exponentially. And of course, you don't want exactly the cosmological constant, because if you plug in the cosmological constant, it is a constant and it does not change. So then the phase of inflation will go on forever and you will not generate your actual universe. So what you want is the value of h should be approximately constant in this period, so that you have an approximately exponentially expanding or accelerating expansion. And afterwards, you want your inflationary period to end, and then standard cosmology to take over. Okay, so it's a tall order, and you can see that it is becoming more and more kind of speculative. This is the way the field has evolved. Okay, so people have, but it's an important enough problem that several people have worked on it and tried to come up with physically reasonable ways of doing this. All of the physically reasonable ways are still observationally more or less untested. Okay, and people still worry about this, and they try to come up with ways in which certain models of inflation can be ruled out. But as you can imagine, since the constraints are so generic, the number of ways in which you can solve the problem are also quite large. Okay, so I will only give you a flavor for what typical models end up doing without going into details of any particular model. So typically, these models tend to produce this kind of inflationary phase around the epoch when the temperature of the universe was 10 to the 15 GeV. This is a sufficiently high energy scale where you will not spoil any of the even high energy predictions that have otherwise been tested either in the lab or in astrophysical experiments. So around this epoch, the value of the scale factor is approximately 10 to the minus 28. So it's really a very early time. And the time that the cosmic time is about 10 to the minus 32 seconds after the Big Bang. So we are talking about extremely early epochs. The co-moving Hubble radius at this epoch, if I extrapolate standard cosmology back to this epoch, okay, through the standard phases, then the co-moving Hubble radius at this epoch is 10 to the minus 26 of its current value. Okay, so that is the constraint, which means that suppose I want the largest observed scales today to have been causally connected around this epoch, because this is the epoch where I want inflation to occur. So then, in order to do this, prior to this epoch, the amount of inflation that I need will be approximately log of 10 to the plus 26. Okay, so that I create a 10 to the plus 26 amount of inflation, and then standard expansion will give me 10 to the minus 26, okay, in the Hubble radius. So log of 10 to the plus 26 is 60 e-folds. So I need 60 e-folds of increase in the scale factor during inflation, because during inflation, the co-moving Hubble radius is just 1 over A. H does not actually change. So these are the constraints that I want. So if I can set up 60 e-folds of inflation, then I will solve the horizon problem. Okay, because the largest observed scales today will become causally connected. So I will easily explain the fact that the CMB is the same across the sky. Okay, so this is what I require. And I also want that the co-moving Hubble radius should have been large enough at the start of inflation. And this is not a problem because the currently observable universe, which is size 10 to the 28 centimeters, in this situation will arise from a 10 to the minus 26 centimeter patch. So at the start of inflation, demanding that a 10 to the minus 26 centimeter patch should be causally connected is a relatively small problem. Okay, it is much, much smaller than demanding that a 10 to the 28 centimeter patch should be causally connected. So this is the kind of stuff that you want. And now you can ask, how should I go about doing this? What mechanism can I invoke? And one of the simplest mechanisms that people have worked with is the idea of a single scalar field. Scalar field, just because it is simpler than a vector field. Vector fields we are used to in particle physics. Scalar fields are simpler to handle. And now we also know that scalar fields, at least one scalar field exists in the universe. This is the Higgs boson. Okay, and in fact, there are models of inflation which try to use the Higgs boson as the inflaton field. These are pretty complicated models because the demands on them are very, very high. Most models don't make this assumption. They say maybe there was another scalar field, not the Higgs, which behaved like an inflaton. And then there are many other models also later which they use multiple scalar fields, etc. So we will not go into details of these things. Let's use the single scalar field model. What is the requirement? This single scalar field should be such that it produces a Hubble parameter which is approximately constant. Okay, and the way this can be done is by asking for what is called a slowly rolling scalar field, in the sense that the scalar field should be slowly rolling in a very flat potential. So let's unpack some of this terminology. So if you go and look up Landau-Lifshitz, they will tell you that the energy momentum tensor for a scalar field has this particular form in general, okay, based on the general definition of an energy momentum tensor in terms of the Lagrangian of the scalar field. So you can derive this expression from the Lagrangian of a scalar field. And the Lagrangian typically has a kinetic term and a potential term. That is where these things come from. And now if I use this energy momentum tensor, what I will find is that in the homogeneous and isotropic universe that I want to populate with this scalar field, the potential, so I am not allowed to tolerate any spatial variations of the scalar field. I can only allow time variations. And then that fixes for me the fact that this energy momentum tensor will naturally have the perfect fluid form. So it will be diagonal with a rho in the 0, 0 term and a minus PPP in the spatial terms. Okay, and no off diagonal elements. So I can also further calculate the energy density and pressure now in terms of the scalar field itself and its potential. And this is where this idea of slowly rolling will come in, because what you find is that the energy density is phi dot squared over 2 plus V of phi. This is like an total energy, kinetic term plus potential term. And the pressure, interestingly, is phi dot squared over 2 minus V of phi. It just follows from this definition. So now the reason I want things to be slowly rolling, I have not written down the equation of motion for the scalar field, which also you can write down. But basically, I don't want this potential to be very steeply increasing or decreasing. Because if that happened, then you can imagine if I have a gravitational potential and a particle is moving, and if the potential is very steep, then the particle will move very rapidly. And if the particle moves very rapidly, then this phi dot squared term will become comparable to V of phi. Okay. I don't want that because I want my h to be approximately constant, and that will happen only if phi dot squared is much smaller than V of phi, because in that case, both rho and p will be related to V of phi, and in fact, p will be approximately minus rho coming from these equations, if I set phi dot squared to 0, for example. And p equal to minus rho is the equation of state of a cosmological constant. So if this kind of field dominates the expansion of the universe, then h will be approximately constant. Okay, so that is the reason for demanding that the phi dot term should be small, and therefore the field should be slowly rolling. And now, like I said, a successful model, even if I arrange for this, it is not enough, because I need this phase of the evolution to stop at some point, and the inflation period should end. Not only should it end, I should generate standard model particles also. Otherwise, where will my electrons and protons and everything else come from? Okay. So during this phase, there is only the inflaton field. After this phase, I need electrons, protons, and well, not even protons. I need quarks, gluons, all of the high energy particles to appear, photons to appear. So this what has to happen is that this inflaton field has to get converted into the standard model particles. Okay, and also a huge amount of entropy should be transferred from this inflaton field to the plasma. Why? Because during this phase, the total entropy of your, the total entropy, if you think about it from the point of view of the temperature of the universe, there is no temperature as such because there is no plasma that you can talk about. But a huge amount of entropy must be put into this plasma that you are creating. Otherwise, the scale factor, which has exponentially decayed, will imply that the entropy of the universe is very small. Okay, but you want to be able to start from a radiation dominated phase which had a substantial amount of entropy, and then that entropy will decay over time. But the initial conditions have to be properly introduced. Otherwise, Big Bang nucleosynthesis will not work. So all of this stuff here, it goes by the name of reheating. Reheating in the sense the universe expanded exponentially during inflation and became very cold. Now you have to reheat it so that it can again become cold up to 2.7 Kelvin today. 10 to the 15 GeV is what it should be heated. Good. So these are the constraints on inflationary models that have to be met, and there is a whole literature on exploring how to build successful models of inflation. And at least one nice thing that happens is that as a very trivial byproduct, the flatness problem becomes solved. And that is simply because if I just go back to the flatness problem argument, there is this business of why omega curvature, why the value of omega a minus 1 is very small at early times. This is not an issue because in the model where the inflaton dominates, omega gets driven to 1 very rapidly, okay, exponentially fast. So in this kind of model, I do not have a flatness problem. But this is still, like I said, flatness problem is not a particular problem to begin with. Solving it is good, but it is not like you did something very great. What is much nicer, actually, is that despite the fact that there is a lot of uncertainty and speculation in how you build an inflation model, generically, whatever kind of inflation model you build, if you argue that there must have been quantum fluctuations on this scalar field at the time of inflation, these quantum fluctuations, due to Einstein's equations, will couple to the gravitational potential. Okay, or in other words, small fluctuations in the energy momentum tensor due to quantum effects in the inflaton field will couple to the classical metric that you are using in the Einstein equations, and they will make the metric depart from the usual FLRW form by a small amount. So you'll generate small perturbations of the FLRW metric. The metric is the way we describe gravity. So basically, you are generating tiny fluctuations of a gravitational potential. Once you have a gravitational potential which is fluctuating by some amount, those fluctuations will immediately couple to any standard model particles that you generate, even if you generated them with perfectly homogeneous distribution. Okay, so the standard components, the photons, the protons, electrons, everything will start coupling to gravity. And this is what forms the seeds of the eventual large scale structure. So there were questions in the previous lectures. Where do the seeds for the sound waves come from? The answer is this. Quantum fluctuations during the inflationary phase are the seeds of the later fluctuations that we see in the CMB anisotropies and then which later grow into the cosmic web. Okay, so this is what I wanted to say about inflation. I want to spend just one slide on the statistics of these initial conditions. So I said that there are tiny fluctuations. So we want to understand statistically what these fluctuations should look like. And most inflationary models, they predict, at least the simpler ones, where I have a single field which is slowly rolling. They very cleanly predict that these initial fluctuations will have an almost Gaussian distribution as their distribution. So these are going to be random fluctuations which are going to be approximately Gaussian distributed, very, very close to being Gaussian distributed. So the way one usually describes this is in terms of what is called, don't worry about this nomenclature, it is in terms of of a coordinate invariant or gauge invariant curvature perturbation. And this, it's called zeta, and this zeta is predicted to be an almost Gaussian random field. So let's study what a Gaussian random field means. Usually a fluctuation field in cosmology is typically studied in terms of its Fourier transform. So I'm sure you know what this Fourier transform means. And remember the Fourier components here, they are complex numbers, and they have a real and imaginary part. And the way this is set up is that for every mode k is a wave number. So k has units of inverse length. And you can think of this as the wave number for the sine or cosine waves. This is the frequency of those waves in space. Okay. So for every value of k, this is a vector quantity. So for every vector that I choose, I have a real part and an imaginary part, or I can have a amplitude and a phase. And demanding that this zeta should be a real field places some constraints on the real and imaginary parts of the Fourier conjugate. So, for example, a of minus k should be a k, and b of minus k should be minus b. So that my zeta minus k is zeta star k, so that my zeta of x is a real. And the Gaussian randomness comes from saying that these AKs and BKs, which are for every vector k, I have a number AK and a number BK given to me. These two numbers should be Gaussian random numbers, and they should be independent Gaussian random numbers. So we know that a Gaussian variable is defined completely by the value of its mean and its variance. So for every k, I have to tell you what is the mean and variance of this A and B. And the way the Gaussian random field is set up is to say that the mean should be 0 for all of them. And the variance is some function of the magnitude of k. Okay, it's called p zeta of k. It's called a power spectrum. And written like this, what will happen is that if I take the 2-point function of zeta with itself for two different values of k, I will see that if k is not equal to k prime, then these two quantities will be uncorrelated with each other, or because this is a Gaussian field, they'll be independent of each other. And if they are the same, then I will find that the variance of this zeta k is given by this p zeta of k, this function p zeta of k. Okay. And also this particular structure, the fact that there is a Dirac delta in k minus k prime, and there is a magnitude of k appearing in p zeta. This is the statement that there is statistical homogeneity because of this Dirac delta, and also statistical isotropy because this p zeta depends only on the magnitude of k. Okay, so these things, if you don't understand, you can ask me later. These are very standard things about Gaussian random fields. The only unknown here is the functional form of p zeta. Okay, so this particular function is predicted by typical models of inflation. So, for example, in simple slow roll inflationary models with single scalar fields, this function is predicted to be a power law, where this k cube p zeta, this is a dimensionless power at mode k, and this is expected to be almost independent of k. Okay, it is usually written like k to the power ns minus 1, where ns minus 1 is a very small. And this is related to a parameter in the physical model typically, which controls how slowly this field is rolling. So the closer this number is to 1, the slower this field will roll. Okay, and this number is now observationally constrained to be something like 0.03 or so, this difference from 1. Okay, so this is just to connect the statistics of the initial conditions with the idea of inflation. And that is basically all I had to say about inflation. So, in fact, let's see if there is a question about inflation. I can answer it now before moving to it. So, Shubhrato has asked, what are the observables of inflation, reheating, and entropy creation? That is interesting. So, with reheating, as far as I know, currently I mean, the way one usually argues this is to say that reheating should not spoil the remaining observations of the Big Bang nucleosynthesis, etc. So it should occur at scales and epochs where it will not spoil what has to come later. Okay, but I do not know, I may be mistaken, but I do not know of any observational prediction of the reheating model, because the whole point is to push all of reheating under a rug so that you don't have to worry about it. Okay, if you had to worry about it, then things would have become more complicated. But I may be wrong. So it would be good to also check with some experts on inflation. So there are people, for example, some of the associates of IUCAA, like Shriram Kumar at IIT Madras, they work on inflation, or there is also I'm forgetting some other names, but like people like this will, for example, be able to answer these questions a little bit better. Okay, but this is what I currently understand. So I think there is nothing else that I can see. So let us move on. Okay, so this is now the second half of the talk, where I want to discuss alternates
Okay,
to
but this
the standard cosmology. So we are coming back now, we are leaving behind inflation, and we are coming back to later epochs, radiation domination, matter domination, and later on dark energy domination or cosmological constant domination. So let us see why we should worry about this phase of the universe. First of all, you could argue that a cosmological constant is allowed by the symmetries of GR. Einstein was the first to recognize this. So you may treat it as a fundamental constant of the universe, which should take some value, and you have gone out and measured it, and it is some value. Okay, when you convert it into omega, the omega lambda is about 0.7, and maybe we should be happy with this. And some people do take this point of view. Other people take the point of view that you have to think a little deeper about what GR is telling you. So GR tells you that all forms of energy gravitate. Okay, so this is a different approach to the cosmological constant. We'll come to the cosmological constant in this argument in a second. So I'm taking a step back and just studying or asking what is GR telling me about the physics of different energy components. So GR says all energy components should gravitate. Quantum field theory tells me that there is a notion of a vacuum. The vacuum has energy in it. When you do standard quantum field theory in a Minkowski spacetime, any calculation of the vacuum energy density turns out to give you infinities. However, in Minkowski spacetime, you are allowed to renormalize the values of your infinities once. So you can do a subtraction. And the reason is that you are only observationally sensitive or experimentally sensitive to differences in energy. So you are never sensitive to the 0 point of the vacuum energy. And therefore, even if the 0 point is formally infinite, you can argue that I will subtract out this infinity using some renormalization procedure. Okay, so it depends on it depends on it's a question of taste. Which renormalization procedure you like? You could impose a cutoff in your integrals at high energies, or you could say I want to do dimensional regularization or some similar equivalent technique. And the nice thing about doing QFT in flat space time is that all these regularization techniques will give you the same answer at the end of the day for the physically observable quantities like electron mass, etc., etc. So you don't have to worry. With GR, there is now a problem because GR says that all forms of energy should gravitate. So now, if I calculate if I do some regularization technique and I calculate a value for the vacuum energy, which is not infinite, that value of the vacuum energy is now available to couple to all of the rest of the universe through gravity, because that vacuum energy, in a semi-classical sense, should be gravitating. Okay, so this is an idea that people had. Like I said, the seeds of this idea actually go back to Lemaitre. Even before QFT was developed, he was basically just waving his hands a little bit. But after QFT came into being, people like Zeldovich, for example, did such calculations. So what they say, so Zeldovich's calculation from 1968, for example, proceeded along these lines. It basically said, let us calculate the expectation value of the vacuum energy using a regularization scheme in which I place an upper cutoff to my momentum integrals. So you say that my cutoff is k, and then the vacuum energy will be a number which is proportional to k to the power 4. So now the question becomes, where do you set the momentum cutoff? And this becomes a question of taste to some extent. Because suppose I say that I trust my semi-classical quantum field theory calculations all the way down to the Planck scale, all the way up to high energies corresponding to Planck scale, then the value of the vacuum energy that I will get will be something like 10 to the power 19 GeV to the power 4. Energy density in natural units has energy to the power 4 units. So the value of energy corresponding to this is 10 to the 19 GeV to the power 4. But the observed value of the cosmological constant, okay, so now I am bringing back the idea of the observed cosmological constant. If I assume that there is a cosmological constant in the universe, its value corresponds to a rho lambda, which is, as you know, of the order of rho critical at the current epoch. And that turns out to be 3 milli electron volts to the power 4. All right. So what do we have? We have a vacuum energy density calculation, which is 10 to the 19 GeV to the power 4 if the momentum cutoff is at Planck scale, and a cosmological constant energy density, which is observationally established to be 3 milli electron volt to the power 4. So now comes the problem. If I say that the vacuum energy, because it is a constant, it behaves identically to the cosmological constant dynamically. Okay, it is a constant energy density in the problem. So if it exists and is non-zero, it should behave exactly like rho lambda. So if I say that, okay, I have a duck here and something that looks like, like a duckling there, maybe the duck came from the duckling. So I will say that rho lambda is nothing but the vacuum energy. But then there is a huge issue because the value of rho lambda compared to the value of the vacuum energy is different by a whopping 123 orders of magnitude. So it is not a factor of 123. It is 123 orders of magnitude. Okay, so it's something completely insane. Nobody in the history of physics has come up with a discrepancy of this order of magnitude. Now you could argue, okay, we should not trust our theories all the way to Planck scale. We should only suppose supersymmetry had been found. You would have said that all your semi-classical calculations you should have stopped at the supersymmetry breaking scale. But even that will turn out to convert this 123 orders of magnitude problem into maybe a 56 order of magnitude problem. Okay, what's a few tens of orders of magnitude between friends? No, so it is still a whopping issue. So this is the problem of the value of the cosmological constant. Nobody yet has a convincing answer to this. There have been many attempts, but there is no attempt which is universally accepted as being the answer to this problem. Okay, so this is a big issue. Secondly, there is also this curiosity that if I look at the value of rho lambda today, omega lambda of zero point 0.3, and I consider the value of rho matter today, which is omega matter of 0.7, 0.3 and 0.7 are not very different from each other. So, they are of the same order of magnitude, despite 36 e-folds of expansion with well understood physics. So, if you remember the plot I had shown you at the end of the last lecture, there is this energy density which is falling from 10 to the power 36 or 10 to the power 15 or something in critical units, all the way down to order unity. And then there is the cosmological constant, which is basically sitting at order unity and waiting. And then exactly around the current epoch, when galaxies start to form, this coincidence happens. Okay, the value of rho lambda becomes approximately the same as the value of rho matter. So this coincidence is a little bit too coincidental for some people. So this is called the coincidence problem of the cosmological constant. It is similar conceptually to, at least in my way of thinking, this is similar to the flatness problem. It is probably a question of aesthetics. Other people think it is more serious. But the value problem is definitely a problem. Okay, because you cannot say that vacuum energy is the same as cosmological constant. So there are these two problems. And again, these kind of issues have led several people to start thinking along different lines. Maybe saying that you should not think of a constant answer to the question of the cosmological constant. Maybe the cosmological constant should be replaced with a dynamical component, such that at current epochs, what do you require? You require the value of the evolution of the scale factor to be accelerating. So you can come up with dynamical components which will do this job. And our experience with inflation over the last 30 years has told us how to do this, right? So in fact, that is exactly what then people did. They took that experience and said that let there be a scalar field, and they gave them different names, quintessence, k-essence, etc., which can do this job. You can come into something like a slowly rolling phase, which will produce an inflationary like phase for you. But now it is not inflation, it is an acceleration at the late times, and this will maybe solve the problems of the cosmological constant. So you can do this, and in fact, you can come up with models which very naturally solve the coincidence problem, because you can adjust the parameters so that it becomes very natural for the scalar field to start accelerating the universe only at late times after galaxies form. Great. But you have still not addressed the value problem. Okay, so the vacuum energy problem is still there. So almost, or not almost, every single model of dynamical dark energy will first say, let us set the vacuum energy to be exactly zero due to some symmetries in the early universe which we do not yet know. and then we will come up with the problem, with a solution to the coincidence problem. Okay, so I just wanted to emphasize that no matter what you do, the vacuum energy problem has not yet been solved. It is a completely open problem in the literature. Okay. There are other ways of addressing these issues. People argue that maybe GR does not work on the larger scales. We have only directly tested it on at most, solar system scales, not even at the scale of the full galaxy. So maybe you have to give up on GR and modify it with something which looks like GR on small scales, but then does not look like GR on large scales. So, for example, there are alternative models like FFR gravity, and then some questions arose yesterday about brane worlds, etc. So all of these go in there. And as far as observations are concerned, there is no conclusive evidence yet that any of these models are observationally preferred over a standard lambda CDM cosmology. Okay, there are some papers that are claiming otherwise, but as far as I understand, the consensus is that lambda CDM is still consistent with all the data. So this is a brief history and a description of the problems with the late time issues of the cosmological constant. And now, before I end, I want to give you a little bit of flavor of one particular, completely different alternative to the standard model. It is also a very old alternative. And one of the reasons why I think somebody taking a summer school refresher course at IUCAA should know about this is because it was something that was proposed by our founder director and worked on by this. Not proposed, but worked on. And it was something that it was a strong contender to the standard model for a long period of time. Okay, so it is good to understand this particular alternative model, even if it is completely ruled out today, because it teaches you something about how theories can be built and how observational questions can be addressed. And maybe it teaches us a little bit about how we should be thinking in the current epochs. Even if we think we have a well working standard model of cosmology, we should be critical about different aspects. Okay, so with that motivation, let's talk about the steady state cosmology. So this was formulated by Bondi and Gold in 1948 and Fred Hoyle also in 1948, and then developed further by Hoyle and Jayant Narlikar in the 1960s. So the original motivation was partly due to the then known discrepancies in measuring the age of the universe from H naught. Remember, I told you that Hubble's measurement of H naught was inconsistent with the then known ages of the stars in the Milky Way. And it turns out later that the reason that happened was that Hubble's calculation of H naught was based on an incorrect calibration of Cepheid variables. He had not realized that there are two classes of Cepheid variables. He was mixing them up. And the value of H naught that he got was much larger than it should have been by a factor of 10 or so. And therefore, the age of the universe, which is like 1 over H naught approximately, he was getting wrong by a factor of 0.1. Okay, factor 10 in the wrong direction. So he was predicting T naught of 2 gigayears when the actual age was more like 10 to 12 gigayears for the stars. And then that got solved later when the value of H naught settled into more reasonable numbers. But at the time, there were these discrepancies, and this was partly the motivation for developing a model of cosmology which does not have a Big Bang. But this was only part of the motivation. The main motivation for these alternate models was the fact that standard Big Bang cosmology had an issue. It had a singularity at the origin of time. The theory itself broke down at the origin of time. Okay, so these theoretical and philosophical considerations were what motivated these people to look into other ways of addressing the cosmological issues. So, for example, the notion of the singular beginning was problematic. You cannot set up an action principle if I have a singular beginning. Then the other thing was that in the standard cosmology, one invokes a cosmological principle, which basically says that we are not special observers in space. And that is what allows you to say that the CMB that you see around you should be isotropic. Okay. And the fact that you are seeing an isotropic CMB should not be unique to you because you're not a special observer. So any observer anywhere in the universe should be seeing an isotropic CMB. And then there is a theorem which tells you that if I take isotropy around one point and I demand that isotropy should be there at all points, I will get homogeneity as a consequence. So homogeneous and isotropic space comes out from this cosmological principle. what these people argued is, why stop at space? You should also extend the notion of cosmological principle to time, that you should not be special observers in time either. It's a very interesting concept. It is not used in standard cosmology, where we just say that there is a flow of time and at different times different things happen. If I were an observer at 1 MeV versus being an observer today, I will see very different things. Okay, so the steady state way of thinking was completely different from this. So if I take these two things seriously, for example, the perfect cosmological principle and the idea that I don't want to have singular beginnings, etc., it led to a theory, lo and behold, which had a constant value of the Hubble parameter and the energy density and an exponentially expanding scale factor. The way this was done is by creating matter constantly at a rate which is 3 times h times rho. Notice that this is all happening in the 1950s and 60s, which is at least 20 to 30 years before the idea of inflation. But notice the similarities between these ideas. Okay, so this theory predated inflation by at least 3 decades. So, very interesting fact. And then the whole thing could be described in terms of something called a scalar field, a creation field C, which is basically a scalar field. Later on, it was called an inflaton. So now many other theoretically nice things also happen. So, for example, there are concrete predictions for the distance redshift relation. There is no freedom in the distance redshift relation. It is a non-parametric model. There are predictions for what event horizons should look like, and so on and so forth. There was also something called the bubble model, which actually was extremely similar to what inflationary models look like later. But there was a key difference from the Big Bang model, which is that there was no early hot phase in the universe. And these were two parallel theories which were in place in the mid 1960s, where two key observational events occurred. The first one was that deuterium was observed in astrophysical observations at levels consistent with the predictions of Big Bang nucleosynthesis. If you remember what I told you about deuterium, it is a very tenuous material. So in stars, for example, if you produce it, it will not stay for very long. So if you observe it, it is almost certainly primordial. And not only was it was observed at levels which were consistent within the error bars with the predictions of Big Bang nucleosynthesis. Okay, so that was one very powerful argument in favor of the standard model. And the second argument, which was like the nail in the coffin, was the discovery of the thermal and isotropic CMB radiation. Since the steady state cosmology did not have an early hot phase, it did not predict a CMB. In fact, it predicted that there should be no CMB. And the fact that the CMB was discovered meant that the steady state universe was simply out of the picture. Okay, so this is a very interesting history. The story goes on. I will not go into these details. The theory was tried to, and people, so Hoyle, Burbidge, and Narlikar tried to revive this theory in a different way, in the guise of what's called the quasi-state cosmology, much later in the 1990s. This theory is substantially more complicated than the original steady state cosmology. Steady state cosmology was very beautiful, non-parametric, and philosophically very appealing, etc. The quasi-steady state was built on steady state, but it had more complications. So there were several free parameters, for example, bringing it much closer actually to the standard model of cosmology, at least conceptually. Okay, so but physically it is still extremely different from the standard model. There are many very interesting features. And the one thing that still remains to be understood there is why the CMB anisotropy spectrum should be the way it is. And large scale structure, as far as I know, has not really been predicted very well. It is also true that almost nobody works on this theory anymore. Okay, so I wanted to give you a feel. I've given some references here which you can look at, especially in Arliker's book. This is just a way of opening your minds a little bit. Don't think that the standard model of cosmology is there and therefore this is the only thing we should use. I do that in my work, as in I don't work on alternate models really. But as a researcher, I think it is very important to keep an open mind and to be open to alternate ideas, because maybe an alternate idea will lead to a new discovery at some point. Okay, so you never know where discoveries may happen. So I think that is all I wanted to talk about. I will stop now for this lecture, and I can take some questions. So let's see what is in the chat. Subrat again, is it possible that steady state cosmology holds in smaller time scales, maybe during different epochs when values of observables were more or less steady? Uh, I am not sure about this. So the basic underpinnings of the steady state model are very different. Okay, so it is not clear to me how you would, maybe the quasi steady state is a way of doing this. So this is essentially the philosophy there. But the way you would want to explain CMB, etc., is then very challenging. So I do not think there is any known easy way of doing this. Maybe it's worth thinking about. I don't know. Anything else? That's the Google sheet. So I don't see anything new in the Google sheet either. All right. So if there is nothing, let us end for now, and I will meet you in the last lecture. In the last lecture, 30 onwards, I will briefly discuss the growth of structure. This is anyway a topic of Tirthankar Roychodhury's lectures, so I will only give you a brief overview. And in any case, it is good to see things from different perspectives. Okay, so he will do things in a different way. I will give you a much more condensed overview of the field. So we'll talk to you later. Okay. All right.